Okay, continuing on to the given problem number 3, which was to solve geometrically the system x minus y equals 7 and x times y equals 18. So we draw ourselves a rectangle. It's going to be x by y. And here up here we've got a square, y by y square here. And this side here is x, so here is y. So this is 7, right? And so we see that x minus y equals 7, and this area of this rectangle is 18. So what we're going to do is we're going to cut this bottom rectangle in half and place it by the side up here, and then fill in with a little square. So we create this gnomon here. Okay, so since we cut the 7.5, this is 3.5, this is 3.5. So now we've created a square. It's a y plus 3.5 square. So its area is y plus 3.5 squared. And the area, another way of doing it is the original rectangle, which is 18, and also the area of the gnomon, plus this little square we've added of 3.5 squared. So we add those together, we get 30.25. So square root of 30.25 equals y plus 3.5. So that's 5.5 is the square root of 30.25 equals y plus 3/2. So that means y equals 2. So that means x has to equal 9. Okay, going on to question number 4, which was to do the double reductio ad absurdum argument. Okay, so we want to do things finitely. So let's consider the finite sum of going up to from 1 plus a quarter squared all the way up to a fourth to the n. So the standard trick here is to multiply that by 4. And so you get 4Sn on the left, and on the right you get 4 plus 1 plus a quarter squared, etc. It's 4 plus Sn if we subtract off. So if we add 1 over 4 over n, we've got Sn. So if we just subtract 1 over 4 to the n, we get that. Okay, so that means we can solve that for Sn. We get 3Sn equals 4 minus a quarter to the n. So the sum up to 1 over 4 to the n is 4/3 minus 1 over 3 times 4 to the n. Okay, so we want to find out what this limit is. We want to show that the infinite sum is 4/3. So what we do is first assume, well, what happens if it was less than 4/3? Right? If it was less than 4/3, then there is an actual number such that 4/3 minus that number equals some positive integer. Okay, but so there's an epsilon, but the thing is we can make the difference between Sn and 4/3 as small as we like, because we've got that factor 1 over 3 times 4 to the n. So if we just choose n large enough, we can make 1 times 3 times 1 over 3 times 4 to the n smaller than epsilon. So that means our finite sum is bigger than what we think the limit is. And that's a contradiction, right? Because it's that sum is monotonically increasing. Well, what happens if we assume that the sum is greater than 4/3? Well, if the infinite sum is greater than 4/3, then we must have some finite sum which is greater than 4/3. But 4/3 minus 1 over 3 times 4 to the n can never be greater than 4/3. So we can't have L being less than 4/3, we can't have L being greater than 4/3. So by the law of trichotomy, L actually equals 4/3. Okay, so the fifth question was to talk about Archimedes and nuclear weapons. I was kind of interested in what your opinions were. So a lot of you agreed that that for defensive purposes it was okay. I mean, because that's what Archimedes himself did. But for attacking weapons, that maybe Archimedes didn't have to have anything to do with that. And I was kind of interested in people bringing up things like, you know, Los Alamos in the Second World War with nuclear weapons, or, you know, working on, you know, bioweapons, working on gas, you know, maybe talking about Fritz Haber during the First World War, who designed poison gas for warfare, stuff like that. Anyway, the last problem was work of Archimedes trisecting an angle. So why is this not a straight edge and compass thing? It was in the thing we were told you have to find this line segment PB such that PQ equals R, and that's the bit that you couldn't do by straight edge and compass. And then to prove that it trisected, so by now we'd had seen a few examples of this where you kind of use isosceles triangles, and so we see that that there's a lot of line segments which are radial length, so that means there's a lot of triangles. So there's actually around 3 there that we can produce, but there's only 2 that we're interested being isosceles triangles. So alpha is the thing that we want to trisect, right? And so if we call this angle in this in the triangle OQB, we call that X, and if we let the equal angles in the triangle PQO be Y, right, then OQP, is that OQP, right, that's going to be 180 minus 2Y, but that's also 180 minus X, so 2Y equals X. BOQ, this angle here, is then 180 minus 4y, right? Because this is 180 minus 2x, so that's 180 minus 4y. So then we've got alpha plus 184 minus 4y plus y equals 180. Well, that tells us that alpha equals 3 times y. So y is the trisection of alpha. And that was our homework assignment.